So I was just saying to Daria that I made a couple of small mistakes last time, and also added some stuff to the lecture notes afterwards. So there's this one. I wanted to work out explicitly what this lemma meant in 2 dimensions, because it was a little bit of a black box. The I del bar lemma. So remember what it says. It says that if you've got a 2 form on your complex manifold, which is closed and which is living in the 1-1 part, then actually it can be expressed as a sort of a double derivative of a del bar of a function phi. We know that locally, so if it's closed, then we know that locally alpha is d of a 1 form. Now I was saying something much more powerful. We're saying that it's a del bar of a 0 form. And that the proof relied on this, so first of all, the usual Poincare lemma, which is fine. But then at some stage, you need to know that if del bar of a form is 0, then you can write it as del bar of a function. So this is this sort of holomorphic Poincare lemma, which I didn't prove, but I stated. So then I wrote this out. And then I said, okay, so in 2 real dimensions, what's going on here? What the theorem is saying is that if you start with a closed real 2 form of type 1-1, obviously you're in 2 dimensions, so it's always going to be closed because there aren't any 3 forms. But what is a type? So it's just saying that if you start off with a real 2 form of type 1-1, what does that mean? A type 1-1 form is going to be some smooth function times this dz wedge dz bar. So it's just an arbitrary smooth function times dz wedge dz bar. That's what I'm starting with. Then the theorem is saying that I can express alpha as del bar of something, or I del bar of something, right? And I del bar, if you go and work it out, what does that mean, right? It's going to be the Laplacian, right? Because if you do del is sort of del x minus I del y, and del z bar is del x plus I del y. So if you do the composite of that, then you basically get this Laplacian, the second derivative of phi. So in very down to earth terms, it's saying that any real smooth function f basically can be expressed as the Laplacian of some function phi. That's what it's saying in this situation. So I have to solve a PDE, right? So I have to find a phi such whose Laplacian is equal to f. And this can be solved. This is Poisson's equation. And you can use it, you can solve for it using Green's functions and something called the Poisson kernel. So I may be mistaken, but I think this is an explicit formula for how you would solve it on the unit disk, for example. Right, so just to show you that it's sort of non-trivial, the statement of the theorem, right? But it comes down to solving a PDE. In terms of a physics analogy, what it's saying is that I guess so you're given F and you want to solve for phi. I guess phi is going to be the electric potential or something, and then F is going to be your charge density. Somehow you're given the charge density and you have to find the electric potential, and there's some getting mistaken there. And at least in physics terms, we know that if you put some charges on the unit disk, then there is going to be an electric potential. So that's a sort of physics proof of the existence of phi. Yeah. And that's how the sort of fathers of complex analysis would come up with these sort of proofs of the existence of these functions. They would use these electrostatic analogies. Okay, so there was one other thing I just wanted to point out from my corrections from last time. Yeah, so I got some factors of 2 mixed up here, and they're important factors of 2. So what were we doing here? We were looking at the Kähler metric on S2, and then since we've got a Kähler metric, we've got the associated fundamental 2 form, or the Kähler form. Talking in terms of the metric or the form are interchangeable, right? And then we calculated the integral of that form, that 2 form over S2, and we got the area of the 2 sphere as we'd expect, 4 pi. And then I calculated that in various ways as well. So I also calculated in the z bar coordinates. And in terms of the del bar lemma, so you got this, whenever you have a Kähler metric, then you have this potential, and the potential can be written like this. When you calculate del bar of this, then you get this here, which makes you think, well, why do I want that 2 there? It makes you think that a more natural symplectic form would be this one here without the factor of 2. And that's indeed the case. So there's a more natural symplectic form living on the 2 sphere. I should rather say when I think of the 2 sphere in terms of CP1, the more natural 2 form that lives on it is not the one whose integral gives you 4 pi, but it's the one whose integral gives you 2 pi. Okay, and we'll see that again in today's lecture. Yeah. All right. So I also then wrote out explicitly what the Kähler structure is on CPN. Yeah. And in particular on CP1, here's the 2 form. You see it doesn't have a factor of 2 in front. It's just got a factor of 1. So when you integrate it, you get 2 pi, not 4 pi. Okay, so let's start with today's lecture. So I want to speak about complex line bundles with connection. Good, so a lot of this is from Le Floch, but some of it's from another reference called Schottenloher, which I will give the reference for just now. So first of all, recall that a complex line bundle over a smooth manifold is a one-dimensional complex vector bundle over the manifold, right? We spoke what vector bundles are, so one-dimensional complex vector bundle is called a complex line bundle. And remember that a smooth section is just a smooth map, such that if you do the projection after the section, then you get the identity. And also 2 line bundles are isomorphic if there exists a diffeomorphism from L to L prime, which is compatible with the projection maps, and which restricts to a linear map on each fiber. Okay, why am I talking about line bundles now? I wanted to speak about the nicest possible geometric situation. So a Kähler manifold is a very nice example of a complex manifold. So it's a complex manifold where you've got a compatible Riemannian metric in a very nice way, right? Compatible meaning that the Riemannian metric is compatible with the almost complex structure, so it's compatible with the infinitesimal data, but it's also compatible with the local data, meaning that parallel transport of the almost complex structure preserves the almost complex structure. And I want to now today speak about an even nicer situation where the Kähler, with the metric, the Kähler metric, or alternatively the Kähler form, this 2 form, doesn't just arise. At the moment, it's just sort of some 2 form that we just haul out of thin air. We just write it down for any given manifold. But we'd like that 2 form to arise from some other, even more canonical geometric structure. So we'd like it to arise as the curvature of a line bundle. living on the manifold. Then we're in the nicest possible situation. So I need to describe line bundles to you. Okay, so all of this is the global description of line bundles, but there's a local description of line bundles given in terms of co-cycle data. So let's see how that works. So suppose you're given a line bundle L over a manifold M. This data that I'm going to write down now would just as well work for an arbitrary line bundle over a topological space, right? Because the concept of a vector bundle makes sense over any topological space. It doesn't have to be a manifold. So given a line bundle L over M, let UI be an open cover of M, and by definition of the line bundle, you know that there exists an open cover such that there are local trivializations of the line bundle like this, right? That line bundle restricted to each open set UI is isomorphic to a product line bundle of just UI cross C. That's the definition of what it means to be a line bundle, that it's locally trivial. So that means that for each I, we're going to get a local section, going to be a smooth function on UI. Well, it's a smooth section of the line bundle restricted to UI, defined this way, right? It's just, see over here, we have these canonical sections where at each point in UI, I just give the complex number 1. So I've got canonical sections living here, and I can just pull it back to give me a section over here. That's what I've done here. See this complex number 1, it's the constant function 1 each point. So in terms of a picture, here is the trivial line bundle over UI. So it's just literally the fiber at each point is just the complex numbers. And so sitting over there, I've got this canonical unit section, which is just 1 at each point. And then I can pull that back along this trivialization. That's going to give me some section here of my line bundle over the open set UI. So that's what I call SI. Given the trivialization of line bundle, you get these local sections. Notice that this section is nowhere 0. Why?
Well, because it's everywhere 1.
That's not quite precise, because there's no notion of 1 in the lines here. You see, these lines are just.
Sure, yes.
Yeah.
Because your trivialization has to be inversible.
Right. More precisely, it's a linear, restricted to each fiber, it's a linear map. So that would mean it cannot, this guy here is non-zero. See, the concept of 0 is only a concept that makes sense in a vector space, right? So this guy is not equal to 0 in the complex numbers thought of as a vector space. So since I've got a linear isomorphism between this vector space and this vector space, this guy can't equal 0 inside this line either. That's the idea. So now notice that these sections aren't just some arbitrary local sections. On the intersection of UI with UJ, we're going to have that Sj equals Gij times Si, where these Gij are called the transition functions. So they are actual smooth functions defined on the intersection of UI with Uj, and they take values in the non-zero complex numbers, because they define, literally, you just take the quotient of Sj over Si. I can do that, you see, because this guy is an element of a one-dimensional vector space. This guy is an element of a one-dimensional vector space. Both of these are non-zero elements in that space, and particularly this guy is non-zero, so I know that this guy can be written uniquely as some complex number times that guy. I'm not taking the quotient of 2 complex numbers here. I'm taking the quotient of 2 non-zero vectors in a one-dimensional complex vector space. But the result will be a complex number. So just as the picture, yeah, I've got my blue section and I've got my red section. And the red section is some multiple of the blue section. Non-zero multiple. So if you want to write these Gij, these transition functions, which is the data that I've extracted from the line bundle now, I could write it down in terms of the original Right now, I've calculated in terms of these local sections. The local sections were calculated from the local trivializations, so I could write it all out in terms of the local trivializations if I wanted to. Then I would write it like this. Okay, but it's nicer to work in a sort of two-step process where you first of all think in terms of these local sections, and then, should I say, local non-vanishing sections. And then the GRJs are the functions which take you from the one to the other. Okay, and here is a cool thing, is that these transition functions aren't just arbitrary transition functions. They're going to satisfy some equations on the various intersections of open sets. So first of all, GII has to equal 1 on UI, because GII is going to be SI over SI, so that's 1. On the other hand, on UIJ, what does this mean, by the way? That just means UI intersection UJ. That's just a shorthand for that, right? Gij times GJI will equal 1, because this is equal to SI over SJ, and this is equal to SJ over SI, so they cancel, you get 1. And similarly, product of Gij with GJK times GKI will also equal 1, again, because, yeah, this is SI over SJ, this is SJ over SK, this is SK over SI, and then it all cancels to give you 1. So this is on triple intersections now. Right, so from the Lamb bundle and a local trivialization, I've extracted out these transition functions. And this is somehow, these transition functions capture the data of the Lamb bundle up to isomorphism. But let's first do an example. So consider the S1. It's a nice manifold, right? One sphere. And let L be a square root of the tangent bundle. So over here, I've drawn in blue the sort of a basis for the tangent bundle of the two sphere, right? Of the one sphere, sorry. So at each point, it's just the lines that are tangent at that point, and there's actually a globally defined section of that tangent bundle, right? There's these blue vectors. And then in red, I've drawn a square root of that, in the sense that, think of this blue vector as living inside a complex plane here. And what would be the square roots of this line here? In other words, what are all the points in the complex plane which square to land on this line? It would be all the points lying on this line with 45 degrees. So this is actually a one-dimensional real vector space. So for now, I'm talking about real vector bundles. But anyhow, here is this line that I'm going to attach to this point. And over here, that's going to be this line, because these guys, when you square them, they give you that. Note that I could have also spoken about the other square root of the tangent bundle, because I could have, for example, have my tangent vectors pointing downwards, and then I would be taking this square root here. So I have chosen this particular square root of the tangent bundle here. It's these red vectors. And just from the picture, you can see that this is not a trivial line bundle, in the sense that there's not going to be a smooth, nowhere vanishing section of L, right? Because if you try and do it, you're going to run into trouble. Whereas there is this section of the tangent bundle. Yeah. So just to write it out explicitly, the tangent bundle would be the real vector space spanned by these blue vectors. That's these vectors here, unless I've made an error. And then the red line bundle is the real vector space spanned by these vectors. These vectors here aren't a global section. They sort of go over to minus themselves when they come around. So it starts like this, and then it's like this, then it's like this, then it's like this. By the time it comes back here, it's pointing the opposite direction. But the span of that vector is well defined. Okay, so the line bundle is defined, even though it doesn't have a global section. Okay, so this is a real line bundle, but we could tensor it with C to make it a complex line bundle. if you do that, then it becomes a trivial land bundle. So, but at least mentally, let's just think about this particular land bundle, this real land bundle. So it doesn't have a global non-vanishing smooth section, but it does have local sections, right? So if I remove the South Pole, then this would be a smooth section, no vanishing of this land bundle. If I remove the North Pole, then this would be a section of this square root land bundle. Notice I can't extend it to the North Pole because I'm going to get into trouble over here. Like, yeah, I can't extend it to the South Pole because I'm going to get into trouble over here. So if I wanted to calculate the transition functions for this land bundle, well, it's going to be a function which is defined on the intersection of U0 with U1. The intersection of U0 with U1 consists of two pieces, right? So on the one piece, the transition function is +1, and the other piece is -1. Right? Because if you look over here, the red vectors are equal to the brown vectors on the right-hand side here. But on the left-hand side, the red vectors are equal to minus the brown vectors. So that's an example of a transition function. Right? +1 here and -1 here. Of course, generally it could be an arbitrary non-vanishing smooth functions. Yeah, it's actually sort of locally constant, but anyway. Okay, and another example to keep in mind, this will be a line bundle now, a complex line bundle. So consider the tangent bundle of the two-sphere, my favorite complex manifold. For now, just a manifold. So at each point, I've got this tangent space. That is a complex vector space because I've got this J, this almost complex structure living on the two-sphere, which just rotates vectors by 90 degrees. And that would turn this real two-dimensional real vector space into a one-dimensional complex vector space because J can be interpreted as multiplication by I. So this is a one-dimensional complex vector bundle over the two-sphere. And then the exercise is just to work out the transition functions of this bundle using those two charts that we usually use, stereographic projection from the North and South Pole charts. Okay, so I claim that the transition functions completely encode the line bundle up to isomorphism. More precisely, so suppose you're given some of this co-cycle data. So you've got your manifold, then you've got an open covering, and you've got a bunch of transition functions, right? Satisfying the co-cycle conditions. So you've got smooth functions on UI intersection uj into the non-zero complex numbers, satisfying these co-cycle conditions, these equations here. So if you've got this data, then you can cook up a line bundle, which we'll write like this. And by definition, you take the disjoint union of the product line bundles, UI cross C, and then you quotient by an equivalence relation where the pair X comma Z associated with index I is considered equivalent to the pair X comma Gij of X times Z associated with index J. So just as a picture, so a point in this line bundle is an equivalence class. And you see here, I've glued all these local product line bundles together. So for example, this point here got glued with that point there. And I've just written down the formula. It might not be obvious that this really is a line bundle, that you do need to check the validity of this construction. So, for example, and maybe we can answer this question now, where do the co-cycle conditions get used? Any comments?
Could you perhaps show me the co-cycle conditions again, please, Bruce?
Sure. Oops. Here we go.
Okay, and then the construction? Is it to ensure that tilde is in fact an equivalence relation?
Indeed.
Okay. Yeah.
Okay. So it's got to be reflexive, symmetric, and transitive. Yeah. Good. Great. Okay, so we've got this way of building up a line bundle from co-cycle data. And then the formal proposition would be that if you've got a line bundle and you pick local trivializations for the line bundle, which you know exists by definition of the line bundle being locally trivial, then there's a canonical isomorphism between your line bundle and the line bundle that you can build from this co-cycle data. Namely, it sends a vector v or point v in the line bundle to the equivalence class of a local chart times v. But not times v, sorry, someone's phoning me here. Put that down. That's it. This thing here is just a point there, so I can take its equivalence class, and that would be a point in the quotient space. Okay, so we can go that then sort of justifies partly at least the statement that you can reconstruct a line bundle. Well, that does completely justify that you can reconstruct a line bundle from this local data, this co-cycle data. So that's nice. So line bundle has got a global definition, but it can be expressed in terms of local data. Similarly, a section of a line bundle has got a global definition, but it can also be expressed in terms of local data. So under the above isomorphism, yeah, between a line bundle and the line bundle constructed from some co-cycles, what does a smooth section of the line bundle correspond to on the right-hand side? Well, a smooth section corresponds to a collection of smooth functions on each open set satisfying this equation on the overlaps. You see, because if you've got your manifold M, then we've got a open set UI, and that means we've got a local trivialization SI here. Now, if someone's trying to define a section, let's let this brown thing S be a section. Then over UI, I can write SI as some function Fi times Si. Whereas over Uj, so Uj's got its own section, Sj, I could write S as Fj times Sj. And of course, these two expressions have to be equal on the overlap. So because S is a globally defined thing, so over here, we would have to have that Fj Sj must equal Fi Si. And that tells us that, on the other hand, Sj is Gij/Si. So that tells us that Fj has to equal Gji/Fi. Because I've got to divide by Gij. So that's quite nice. We've got an explicit way of talking about sections as well. It's just good old-fashioned functions, collection of functions on these open sets. That's why we think of a section of a line bundle as being a sort of a quasi-function, in the sense that normally, if you've got a function on a manifold, it's just something which is a machine, which at each point x outputs a complex number. That's what a function is. What is a section of a line bundle? Well, at each point x, it doesn't output a complex number, but it does output an element in a one-dimensional vector space. Now, one-dimensional vector space is, of course, isomorphic to the complex numbers, but there's no natural isomorphism, so it's something slightly weaker than a function. So a section of a line bundle is something slightly weaker than a function, but we can think of it as being a sort of a quasi-function. It's a function theory, a function-like thing on a manifold. And now this proposition is telling us if you really want to think in terms of actual functions, then you can. Then you'd have to then speak locally. So you'd have to talk about functions on each open set that they glue together like this. Let's take this analysis and apply it to the square root of the tangent bundle thing that we spoke about earlier. So what does a smooth section of that line bundle correspond to? So that is actually a real line bundle. That's fine. So according to this analysis, a section of that bundle would correspond to a pair of functions into the reals, one defined on U0 and one defined on U1. So it's not a function from S1 into R, rather it's a pair of functions defined on U0 and on U1. And on the overlap, they don't have to agree. In fact, they must disagree in a certain precise way, because we want that on the overlap, the one function must be equal to the transition function times the other function. So we calculated the transition functions just now. So that means is that over here, so F0 is defined on the over here, right? F0 is defined everywhere here. And F1 is defined everywhere here. And the condition is that over here, F0 must equal F1. And over here, F0 must equal minus F1. Those are the transition functions. Okay. So what have we got? We've got something which is not defined on the whole of S1. It's just it's a pair consisting of something defined here and something defined here. And then it's got this sort of behavior. And we could write this in a different way. We could say, well, a smooth section of this line bundle then corresponds to an ordinary function from the interval 0, 2 pi on ordinary function on that interval. And normally, if I wanted to say that it was a function on S1, I would have to say that f of 0 equals f of 2 pi. I would have to have periodic boundary conditions. But now I've got anti-periodic boundary conditions. It's just another way of sort of writing down this data. I've sort of scaled it a bit and so on. Forgive me. But that's a nice way of understanding where anti-periodic boundary conditions fit in geometrically, because often you're in some situation, and often happens in physics, that someone's got some function on S1, or maybe a product of S1s, and says you've got anti-periodic boundary conditions. And it's sort of weird, because often in that situation, you want to be thinking of that function as living as a function on S1. But of course, a true function on S1 can't have anti-periodic boundary conditions unless it's 0 everywhere, because you'd have to have that f of x plus 2 pi equals minus f of x, and yet you're wanting to have a function that's defined sort of well defined on 0, 2 pi. Anyhow, all I'm saying is that the language of line bundles now gives us a precise geometric way to think of such a thing. It's not a function, but it is a section of a line bundle over S1. So it can be thought of as a function-like thing on S1. So antiperiodic boundary conditions are sections of this square root line bundle over S1. Okay, so we know that because such a function, such a function has to be 0 somewhere, right? Because its value at 2 pi must equal minus its value at 0. So if I draw a graph of this function, here's 2 pi, and here's 0. Whatever the value is at 0, it must be minus that when you get to 2 pi. So notice, therefore, it has to cross 0 somewhere. So such a function has to be 0 somewhere, which shows that there aren't any global sections of this line bundle, which we already knew from the beginning. Sorry, there aren't any global, everywhere non-vanishing sections of this line bundle. Now the question is, when I tensor this line bundle with the complex numbers, is that still going to be the case? Okay, so as a complex line bundle, will this be a non-trivial line bundle? Definitely non-trivial. L is non-trivial as a real line bundle of S1. Will L tensor C be non-trivial as a complex line bundle over S1? Okay. Okay, so so far we've phrased the concept of a line bundle in terms of local data. We've also phrased the concept of a section of a line bundle in terms of local data. And finally, we can say when two line bundles constructed from cocycles will be isomorphic. So you can phrase this all as an equivalence of categories if you like. But so suppose somebody constructs a line bundle from some cocycle data Grj, and another person constructs a line bundle from some other cocycle data Grj prime, both living over the same open cover UI. If they were originally living over different open covers, we could take the common refinement of those two open covers, okay? Then the claim is that these two line bundles are isomorphic. I said they, but I mean the line bundles constructed from this cocycle data are isomorphic if and only if there exists these Grj, this Grj doesn't have to be equal to that Grj prime, but there must exist non-vanishing smooth functions such that Grj prime is equal to this quotient times Grj. Right? So these HRs are defined on the open sets UI. Okay, I should actually give this as an exercise as well. Okay. So that's just all to say what line bundles are in terms of their local data. Now I want to phrase this at a more higher level, speak about cohomology. This can all be stated in terms of the language of check cohomology or sheaf cohomology, two different ways to say it. So for now, we're going to talk about check cohomology. So doing the cohomological classification of line bundles, and a nice reference for this is the lecture notes of Schott and Loher on geometric quantization, the appendix there. Okay. So I've already defined for you one kind of cohomology theory, de Rham cohomology. which is defined on smooth manifolds, right? Remember, it's the kth de Rham cohomology vector space was the closed K forms divided by the image of the D map from K minus 1 forms. Okay. Now I'm going to give you a different cohomology theory. It's called check cohomology. This is quite a nice cohomology theory because it's defined for arbitrary topological spaces, and you can take as coefficients arbitrary abelian groups A, whereas the Rham cohomology was only defined for smooth manifolds and it only worked over the reals or the complexes. Didn't make sense, for example, to ask for the de Rham cohomology with coefficients in Z mod NZ. That didn't make sense, right? But for check cohomology, you can do that. So I have to define what check cohomology is. So let X be a topological space, and U are an open cover of that space. A check cocycle. So it's called check because it's named after, I'm just trying to remember which is named after someone, Czech, who was himself a citizen of the Czech Republic, but his name was Edward Czech. Okay, that's where the name comes from. And that funny little symbol there is just how you write the surnames in Czech. So a Czech K cocycle with values in a discrete abelian group A on this topological space X, shall I say it, on X, is a family of locally constant functions. I'll call it eta. So what it is on these K plus 1 fold intersections, you see there's K plus 1 in open sets that are getting intersected there. And each of those is then an open set in the topological space. And I want a locally constant function from that open set into the discrete abelian group. Now, that just means that it's locally constant. So on each connected component, it's constant. Sometimes there'll be more than one connected component, then you're able to have different elements assigned to the different connected components. Okay. So that's all a check cocycle. I shouldn't have said cocycle. I should have just said check cochain, not a cocycle. Cocycle will be something where D of it is 0. I shouldn't have written Z here. I should be writing, let's call it just B or something like this. Let's go at C. There we go. Okay. So there's a co-boundary map, just like in de Rham cohomology, there was this exterior derivative map. For check cochains, there's a co-boundary map that goes from a K cochain to a K plus 1 cochain. And how does it work? You simply say I've got a K cochain, then I need to get a K plus 1 cochain. So I need to get a function on intersections of K plus 2 open sets, and I just define it like this. See, this is an element of that abelian group, where this hat here means leaving out that particular index. Okay, so let me just do an example here just so that we're clear what this means. So let's take S1, and I've got this as my first open set, and this is my second open set. Okay. So what is a 0 check cochain? It would just consist of eta 0 from U0 to A and eta 1 from U1 to A. Locally constant. So if, for example, A was R, then that would just mean the number that you're associating to each point here is just a constant real number. Okay. Then I'm going to calculate its co-boundary. or that's just going to now give me a 2 form. How am I going to define that? It's going to be something which is defined on intersections now, because a two check code chain is defined on intersections of open sets. So I have to say what it does like this. I'm confusing myself. This is going to be a 1. Sorry, this was a eta was a 0 check code chain, and I'm going to define now a 1 check code chain. So 1 check code chain is going to be defined on intersections of 2 open sets. So for example, over here, I've got U0 intersection U1 consists of this component and this component. And at each of these components, I now have to give a locally constant function. So in principle, I'm allowed to give a different number here than to here. But the formula is that delta eta 0, 1 that means on U0 intersection U1 is just going to be equal to, here's the formula here. So it's just going to be equal minus 1 to the power 0 times eta, where you leave out 0, so that'll be 1, 1, minus or plus minus 1 to the power 1, where I leave out 1. Okay, so that's just eta 1 minus eta 0. Okay, is that clear? So given a red locally constant function, a blue locally constant function, I've got a brown locally constant function on that intersections defined in this way. So for example, if the red number, if the abelian group A was Z, and this guy here was 3, and this guy here was 5, then this guy here would be 3 minus 5, which would be minus 2 here and here. Anyhow, if you square that, then you'll see that you get the 0, because these minus signs are going to sort of cancel each other out as usual. So whenever you've got a sequence of abelian groups and a sequence of maps between them which squares to 0, then you have a cohomology. So that's called a chain complex. So then you can calculate the cohomology of that chain complex. So the kth check cohomology group of X, subordinate to this open cover that we started with in the beginning, is defined to be the kernel of delta divided by the image of the previous delta, as always. So far, I'd like it to be something that I can associate just to X, but so far it does depend on this open cover that I chose. So how can I get rid of that dependence? Well, if Vj is a refinement of the open cover, meaning that for every j in J, there exists an I, which is a function of J, which is living in I, such that Vj is contained in Ui of J. That's what it means to be a refinement of an open cover, right? So whenever you have a refinement, then there's going to be a natural map from check cohomology computed with the Ui open cover to check cohomology computed with the Uj open cover. Is that right? Let me just think about that for a second. I'm a little bit worried about that. It should be contravariance. I feel like this map should go the other way, but we'll check that afterwards. So we define the kth check cohomology group of X, the coefficients in A, as the direct limit over all these maps. So you know in category theory, you have this idea of taking the direct limit. And that's what I'm doing here. That way I'm getting rid of this dependence on the open cover. Okay. That's a formal way of writing things down. in practice, we'll never bother with that direct limit because, happily, if you have what's called a Luray cover, sometimes just called a good cover of your topological space, and by that I just mean that all intersections are contractible, then you don't have to then refine it any further. So then the cohomology computed according to a good cover is just the same as this direct limit cohomology here, sorry. So I only need to just compute it relative to a good cover, and I'm good to go. Okay, so just to go back to our S1, we'd like to have a good cover here, just so that we can compute the check cohomology without making reference to the cover. So I can't take those two open sets anymore, because that wouldn't be a good cover, because if I were to do something like this, then the intersection of these two sets would be this region here, union with this region here, and you see this is not contractible because it consists of two components. So you can't find a good cover of S1 with just two open sets. You need three, and here I've got a good cover here, because the intersection of U0 with U1 is just this region here, which is contractible. U0 with U2 is this region, which is contractible, and U1 with U2 is this region, which is contractible. All right, so let's just write down some examples. So what is a zero chain? A zero chain would just be a collection of three integers, because for each open set, you've got to give a locally constant function into Z. So since these open sets are all contractible, a locally constant function just means a single integer attached to that open set. So I'll have an eta naught over here, I'll have an eta 1 here, and I'll have an eta 2 here. Co-boundary of that zero chain would be a 1, or 1, I would call this a 0 co-chain. It sort of depends on how you're indexing these things.
I'm sorry, Bruce.
Yeah.
I think maybe I just missed it, but a little bit up from where you are now, what does the picture on the right represent?
This was just to say that I couldn't get a good cover with just two open sets, because then
oh, I see, because then the intersections are...
That's right. The intersection wouldn't be contractible because it has two components. Yeah.
Okay.
So yeah, I'm just calculating the co-boundary of eta, which by our formula, here's our formula here, right? We know how to calculate these co-boundaries. So on 0, 1, it's going to be eta 1 minus eta 0. And on 0, 2, it's going to be eta 2 minus eta 0, and so on. So for example, over here, it's going to be the blue number minus the pink number, and so on. But that's over here. And over here, it's going to be the blue number minus the green number. Notice that it's a bit irresponsible of me to say over here, because there's an eta 0, 1, and there's also an eta 1, 0. And they're both defined on this little region here. Eta 0, 1 is minus eta 1, 0. Right? They're associated to an ordered tuple. Anyhow, so what am I busy calculating? Busy calculating the zeroth check cohomology group of S1. I used this nice cover. I knew that it's going to be the zeroth cohomology is just going to be with this co-boundary operator is 0, because there isn't any image of the previous guy, because the previous guy is all 0. So I needed that this delta eta must be 0, right? So that means that each of these guys must be 0. If this guy is 0, that means eta 0 must equal eta 1. If this is 0, it means eta 0 must equal eta 2, and yeah, eta 1 must equal eta 2. So they're all equal to each other, and that's the only condition. So the zeroth check cohomology group of S1 coefficients in Z is just Z. Okay, so the exercise is to compute the first check cohomology group of S1 in a similar way, just sort of by brute force calculation. And I think I thank you for sticking with me for so long. Let's have a 13-minute break. We'll start again at 3:10. Okay, so yeah, just starting again. So just a reminder, we spoke about check cohomology groups of a topological space. What is it? Well, again, it's you have a bunch of abelian groups, and then you have a kernel and an image, and then you do a quotient and a check cocycle. So you're supposed to start off to compute the kth check cohomology of a topological space. You have to start off with a check k cochain, meaning a function defined on ordered intersections of k+1 open sets in the open cover, and you want to use a good open cover, and it's a locally constant function taking values in a discrete abelian group A. I'm allowed to apply it to things like the reals and the complexes, which I wouldn't normally think of as being discrete abelian groups, but I can always put the discrete topology on them. So that means to be locally constant just literally means to be constant there. And so I've got this check cohomology that I can calculate for any topological space. And now we have a theorem which I think will apply for an arbitrary topological space. I don't have to apply it to a smooth manifold, unless I'm mistaken. Theorem says that there's a natural bijection between isomorphism classes of complex line bundles over M and the second check cohomology group of M with coefficients in the integers. So that's nice. You can interpret this theorem as saying in two ways. One, it gives you a calculational way to calculate these isomorphism classes of complex line bundles. Or secondly, it gives you a way to interpret what these guys are, what an element in the second check cohomology group coefficient in Z is. It represents an isomorphism class of a line bundle over your space. Now, of course, we did speak about line bundles earlier, and we gave a sort of cocycle definition here. This one's going to be slightly different. This description here, this was more of a sort of a sheaf theoretic description. We don't have yet, yeah. Whereas now we're going to give a check cohomological description, and you'll see the difference in a second. So remember, in check cohomology, these cocycle, these cochains have to be locally constant. So how am I going to write down this? So what is something in here? Remember, that's something that associated to an ordered triple of open sets gives you a locally constant function on the intersection. So how do I get that from a line bundle? The way you do it is you start with your line bundle. Then from that line bundle, you extract out the transition functions. From those transition functions, you're going to calculate a check 2 cocycle. Okay, how am I going to define this check 2 cocycle? Well, it has to be something which to a triple, an ordered triple of indices gives me a function, a locally constant function on the open sets, on the intersection of those three open sets. So how do I calculate that? Well, first of all, we've got these transition functions for the line bundle. Good, they're defined on intersections. and they satisfy this equation, the co-cycle equation, on the triple intersection. Now, since I'm working with a good cover, this intersection here, this double intersection is contractible. That means you can take a global logarithm of this complex valued function, right? Because if you've got a contractible space and you've got a continuous function out of that into the complex numbers, then you can take a log of that function. Sorry, as long as that function is non-zero everywhere, which indeed is the case, right? Because you can never write 0 as e to the power of something, right? But any non-zero number you can write as e to the power of something. But normally you'd run into trouble if you have a non-trivial topology, because then you could go around and come back to where you started, and you would have picked up a plus 2 pi I. But if every loop contracts, then that's not possible. Okay. So we can choose a global logarithm of each grj on these ui intersection uj's. And so I can take the log of this equation. So it will say that the log of the left-hand side equals the log of the right-hand side. Now, there were some choices involved in taking these logarithms, because you had to sort of choose a base point, and then, each logarithm is only well-defined up to multiples of 2 pi I. So you've got to fix a multiple of 2 pi I on each open set ui, and then that fixes these logarithms. So that means when I look at this equation, I take logs of both sides. It's going to say that log of this plus log of this plus log of this is going to be log of 1. And log of 1 would just be some particular multiple of 2 pi I, because when I calculate, I've got very specific logs that I've chosen here. So when I add them all together, I'm going to get some specific multiple of 2 pi I. Okay, I hope that's clear. I've said it in a slightly confusing way, but I hope it's clear. So this n here is a well-defined integer that I obtain once I've chosen these logarithms for each of the grj's. And that's our check co-cycle. You see, it's an integer associated to 3 open sets, ui, uj, and uk. So that n is our check co-cycle. Okay, isn't that the exercise just to fill in the rest of this proof? But that I've at least given you the map that goes from here to here. Of course, I haven't checked the details here. I'm sure that's a bit confusing when you first see it. I think I've got an example here, so let's do this. Let's have a look at this example. It's not a very nice example, I'm afraid, but it at least does something. So let's go back to the square root line bundle that we were working with. Okay, so remember, to extract out this check co-cycle, you have to first get the transition functions for your line bundle. So here are my transition functions. Remember, they're defined on triple intersections. So here's the intersection of U0 with U2, and we agreed that it's 1 there, it's 1 here, but it's going to be -1 over here, if you remember how this thing works. So to get out this check co-cycle, I'm supposed to then take logs of these g's, right? So for example, to take the log of this, I've got to choose what's log of -1. Well, it's going to be either pi I or 3 pi I or 5 pi I and so on. I'm going to choose a specific one. I choose it to be pi I. Okay. And what's log of 1? Well, it could be 0, it could be 2 pi I, it could be 4 pi I, and so on. I could choose one. And I could choose it to be, just let's say, to be 0, and similarly over here. So that means on a triple intersection, for example, an intersection like this, which is a bit of a silly intersection because it's not, it's U0 intersection U1 intersection with U1 again, but it is something you have to consider. I can't get non-trivial triple intersections here because of the structure of the space, right? U0 intersection U1 intersection U2 is empty. But anyhow, I'm supposed to add these things together, and I'm going to get some integer multiple of 2 pi I. So this guy is pi I, this guy is 0, and this guy is minus pi I. So adding them together, I get 0. In a more complicated example, I might get 5 times 2 pi I, something. Then that 5 would be my integer n that I'm going to attach to this triple intersection. In any event, you'll agree with me that the check cohomology class that I've calculated here is 0. It's because in fact, as a cycle, it's 0. So its equivalence class is also 0. So that's just gives us another proof of the fact that this as a complex line bundle, it's trivial because complex line bundles are in bijection with second check cohomology, and we've just calculated that the cohomology class here is 0. So the 0 cohomology classes here would correspond to the trivial line bundles here, i.e. the product line bundles. Excuse me. Okay. This is a classification of complex line bundles, not of real line bundles. So I'm talking about the complexification of that real line bundle that I wrote down earlier. The complexification is trivial as a complex line bundle. Okay, I've said quite a lot. I've introduced check cohomology, cocycles for line bundles, and so on. Any questions at this point? You might be losing me a little bit. I apologize for that. Why do I write things in terms of check cohomology? It's always nice to have a cohomology theory. You can always then calculate things more easily. Okay, thanks, Dario. So, yeah, let's move on. So it turns out that on a smooth manifold M, check cohomology with coefficients in R, that's an abelian group, right? And you can think of it as a discrete abelian group, is the same as de Rham cohomology. So that's quite remarkable because these are two very different things. Like check cohomology doesn't use calculus at all. De Rham cohomology very definitely uses calculus. So something defined using calculus is equivalent to something which is, I would say, combinatorial in nature. Check cohomology is really combinatorial in nature. It's just got to do with the combinatorics of how the open sets intersect with each other. There's no information in these cocycles because they're just constant functions. They're just little elements of the abelian group attached to each of these intersections. So it's really all the information in check cohomology is residing in how the open sets are intersecting with each other. So the theorem is that on a smooth manifold M, there's a natural isomorphism between the de Rham cohomology and the check cohomology with coefficients in R. And by the way, it will also work with coefficients in C as well. And once again, but check cohomology with coefficients in R or C, again, it's locally constant functions. So it means that on these open sets, you've got, the functions are locally constant. So if the open set is contractible, then it's just a single real number attached to that open set. So I invite you to go and have a look and see how this works in the book of Schotten-Loher. He proves it, but let's write it down just for the case k equals 2, because that's going to be the case we're going to be interested in for the case of Kähler manifolds, right? So let's see how this works for k equals 2. So I'm going to take a Durand 2 co-cycle, which is a closed 2 form, and I'm going to map it onto a checked 2 co-cycle, which is a function, locally constant function defined on triple intersections. So how am I going to get that? To start by choosing a nice open cover of your manifold. How do you know such a thing exists, by the way? Well, unless I'm mistaken, you can rely on the fact that you can find a triangulation for your manifold, completional complex, if you like. And how do I know such a thing exists? That comes from, you can put a Riemannian metric in your manifold and then get geodesic coordinates. And once you've got a triangulation for a manifold, then you can get one of these good open covers, because you can take your open cover to just be you've got these triangles or higher dimensional triangles covering your space, and you just let each UI be an open neighborhood of those triangles. And then you'll agree with me that on the intersections then will all be contractible. Okay, so in practice, you can get these open covers from a triangulation. So for example, if I were to ask you in an exercise, what is a good open cover of the 2-sphere, how would you do it? Well, you need to have a triangulation of the 2-sphere. And one way, you could sort of take a sort of tetrahedron and sort of blow that out onto the surface of the 2-sphere. So that's just like a sort of tetrahedral triangulation of the 2-spheres. So how would that look? Something like this. Okay, and then you've got these. So you got these 4 triangles now, and your open sets would just be open neighborhoods of those triangles, and that they would intersect in contractible way. So you'd need four open sets to get a good covering of the 2-sphere. Anyhow, start with a good covering. Now I'm going to give you a map from Durand cohomology to check cohomology. So start with an element of Durand cohomology. By definition, that's an equivalence class. So I start with a representative for that equivalence class, which would be a specific 2 form on the manifold. In the end, you're going to find that all these choices I'm going to make now do not make a difference to the map. So my first choice is I let omega be a representative for my cohomology class. So since each open set UI is contractible, we know that from the fact that d omega is naught, it would imply, why is d omega naught? Because omega is a closed 2 form, right? So d omega is naught globally. But since d omega is naught everywhere, it means that d omega restricted to ui is naught. So that means that omega is equal to d of some 1 form on ui, which I can call beta I. So omega equals d beta I on ui, for some 1 form beta I living on ui. So maybe it would be clear if I rub this out here. Clear. But maybe the point is that, where does this come from? It comes from Poincaré's lemma, right? If you're on a contractible open set, or if you like on a star-shaped region, if the d of a form is 0, then that form is equal to d of something. Okay. So similarly, let's have a look at these beta i's. Well, what happens on intersections? Ui intersected with uj. Well, then I'm going to have that d beta I minus d beta j is just going to be omega minus omega, which is 0. In other words, beta I minus beta j might not be equal to 0, but its derivative will be equal to 0, because its derivative will be equal to omega minus omega on this intersection. So beta I minus beta j on ui intersection j will have 0 derivative. It's the only place where you can meaningfully talk about beta I minus beta j. And since it has 0 derivative on this open set, and this open set is contractible by the Poincare lemma, it must be the derivative of a function. If you've got a one form which d is 0, then it must be d of a function. So I know that beta I minus beta j is d of some function on ui intersection uj. I call that function fij. Okay, so from this omega, I was inextricably led to these fij's. Of course, there were some choices, like there was a choice in the beta i's. There's a choice in the fij's, right? Anyhow, now we observe that if I calculate the d of these fij's on triple intersection, then I must get 0. Again, because d of fij, this is going to be beta I minus beta j, plus beta j minus beta k, plus beta k minus beta I. So it's all going to cancel out to give me 0. So this one form is equal to, has a 0 derivative on this contractible open set. So this, what am I saying here? Sorry. This 0 form has derivative 0 on this contractible open set. So that means if this function, right, that's what a 0 form is, if a function has 0 derivative, it must be locally constant. That's where I'm linking this idea of being locally constant to calculus, right? That's the fundamental link, that a function is locally constant if and only if its derivative is 0. Okay, that's how I get from combinatorics to calculus. So that means that this number here, which is just the sum of these three functions, see each individual function, that's non-zero, and that's non-zero. Sorry, shall I say this is not constant, this is not constant, and this is not constant, but the sum is constant because its derivative is equal to 0. And since it's constant, I can think of it as being a R-valued check 2 cocycle. Of course, I'd have to check that. I have to check that its delta is 0, but that's something you can check. So that's how I'm extracting out a check 2 cocycle from a closed 2 form on a manifold. So that's how my map works at the level of 2 cocycles. I've started off with a cohomology class in degree 2 here, in the RAM cohomology class in degree 2, and I produce for you a check cohomology class in degree 2. Basically by using the Poincare lemma successively. This method is called the method of descent. You descend down until you get a locally constant thing, which would then be a check cocycle. So putting these two results together, what are those two results? Firstly, the classification of complex line bundles in terms of check cohomology with coefficients in Z. And secondly, the fact that check cohomology with coefficients in R is the same as de Rham cohomology. That means that isomorphism classes of complex line bundles L over M, and this is a mistake here, I said is in bijection with integral elements in second de Rham cohomology. So the mistake I'm making is that there's really just a map from one to the other. Right? Because you see, this check cohomology group here, this might it might compute in some given situation. It might compute, for example, as Z mod 5Z. it could happen, or Z mod 2Z, right? And then that's what's called a torsion subgroup, and that torsion subgroup would vanish when into RAM cohomology. So it's not true that the RAM cohomology can classify the line bundles up to isomorphism. Check cohomology can, the RAM cohomology can't. But each line bundle does have a representative in the RAM cohomology. It might happen that that representative is 0, but then you couldn't conclude that the line bundle was trivial. However, if its check cohomology class is 0, you can conclude that line bundle is trivial. Okay, what do I mean by the integral elements here in the RAM cohomology? I wrote down something slightly weird here. Integral elements in second de RAM cohomology. And this thing here, I'm going to introduce my own weird notation. I'm going to call that the de RAM cohomology of M with coefficients in Z. And what do I mean by that? Earlier I said there's no way you can talk about de RAM cohomology with coefficients in some weird abelian group like Z mod 5Z. But you can actually talk about de RAM cohomology with coefficients in Z, because all you would do is you think of it as a subgroup of the de RAM cohomology with coefficients in R. And which subgroup? It would be the, sorry, I made the same mistake. You got this de RAM cohomology with coefficients in R, and you can ask, what are the integrals? So remember, when you've got a K form, or if, for example, you've got a 2 form, you can integrate a 2 form over a surface in your space. And if that's going to give you a number, and if that number is an integer, then you say that your 2 form is an integral 2 form. Simple. So the integral 2 forms are a subgroup of the, of all the forms. And similarly, that means you get an integral subgroup of the de RAM cohomology vector space. Think of it as like being a lattice inside the de RAM cohomology vector space. Okay. And now what I've shown you how to extract out such a de RAM cohomology class from a line bundle, and it's going to have integral periods. Periods meaning what happens when you integrate this 2 form over a surface. Okay. Long story. Let's just summarize the first hour and a half of this lecture. Is just to say, given a line bundle, you can extract out a 2 form, and that 2 form will have integral periods. That's the summary. Let's carry on. I've spoken about line bundles. Now let's speak about holomorphic line bundles. So before I was just speaking about smooth line bundles over smooth manifolds, or if you like, just line bundles over topological spaces. Right? There's nothing, I didn't need anything about the smooth structure there. Now I'm going to speak about a holomorphic line bundle. So a complex line bundle over a complex manifold is called a holomorphic line bundle if L is equipped with the structure of a complex manifold and pi is a holomorphic map. Okay, so this guy here is going to be also, to have a holomorphic line bundle, your base space needs to be holomorphic, so it needs to be a complex manifold. And we say that L is a holomorphic line bundle if L is itself equipped with the structure of a complex manifold, and that this map pi is a holomorphic map. Okay, so how do I write such a thing down in terms of local data? I know how to write down the structure of a line bundle in terms of local data. What about a holomorphic line bundle? So an ordinary line bundle, we know, in terms of local data, can be expressed in terms of these transition functions, which, if it was just a smooth manifold, then these were just smooth maps into, satisfying these equations. So similarly, if you go through the whole rigmarole that we did earlier, you'll find that for a holomorphic line bundle, these transition functions are going to be holomorphic maps. Okay, and that will classify the line bundle. So a holomorphic line bundle is the same thing as a bunch of holomorphic maps of this kind satisfying these equations. Okay, so the classification of holomorphic line bundles up to isomorphism is more intricate than the classification of just smooth line bundles up to isomorphism, because there is also this holomorphic structure that you have to worry about. You could put different holomorphic structures on L, you see. So let's give an example of a holomorphic line bundle. So I'm going to do the most natural example, which is the tautological line bundle over CP1. So once again, what is CP1? CP1 is the set of one-dimensional complex subspaces of C2. So a point in CP1 is a one-dimensional subspace in C2, and that means it's going to be a natural tautological line bundle living over CP1, defined as follows. See, here's C2. Here is a line inside C2, a one-dimensional vector space. I'm drawing it sort of in the real picture here. I mean, C2 as a space is actually a four-dimensional real space, right? Because it's pairs of complex numbers. Forgive me. So I've just here is a line, one-dimensional line in C2. So it is a point inside CP1. And now associated to that point, I need to give a complex line, because living over each point must be a complex line. And the complex line that I'm going to associate to this point is the line L itself. Okay, that's why it's called tautological. Tautological just means I'm not sure, extreme, so obvious that it's sort of by definition, something like that. So said differently, if you want to write down a more formal description of the tautological line bundle, it consists of pairs L, V, where L is an element of CP1 and V is an element of L. Because L, being an element of CP1, means zero one-dimensional subspace, so it makes sense to say that V is an element of L. Okay, so what are the local trivializations for this line bundle? Because I have to try and convince you that this is a holomorphic line bundle. So remember, for CP1, you've got these two local trivializations, U0 and U1. U0 is where Z0 is non-zero, and U1 is where Z1 is non-zero. So you can use these homogeneous coordinates. So the local trivialization size 0 is going to take tautological line bundle restricted to U0 and give you bijection with product bundle U0 times C, and it's going to send this element of the tautological line bundle to this element here. See, an element in the fiber here can be written as some multiple lambda times this vector. In the picture here, I'm living over the open set where Z0 is not naught. So I can in homogeneous coordinates, I can always make it 1. So I'm living over here. Now someone gives me a line L. That line L is going to, I can always take this particular point, 1, Z. So it's 1 across and Z up. 1, Z is a particular point in that line. And there's lots of points in this line. That's another point, and this is another point. But I'm speaking about this particular point. And any vector can be written as a multiple, in this line is a multiple of this guy. So any vector can be written as lambda times this guy. That's all I'm saying here. And then what I'm going to do is I'm just going to extract out that lambda. That's how I'm going to get this local trivialization. It only works, of course, where this coordinate here is non-zero, because it's not going to work over here. It's not going to work on this line. There's only one, for one line, it's not going to work, and that's going to be on this line here. So in U1 is the points where these guys are non-zeros. And so now I have a different trivialization. Now the basis vectors is not going to be 1, Z anymore. It's going to be Z, 1, which is a different basis vector. Okay. And then so now I'm extracting out a different complex number, mu. Okay, so just to be clear, the local sections, so once you've got your local trivializations, you can translate those into local sections. The local sections are like this. S0 gives you 1, Z, and S1 gives you W, 1. Okay, this is the most, I think, the clearest way to say what's going on. Once you've got your local sections, you get your local trivializations by just saying, well, this section is equal to something times this section. That's your local trivialization. So let's work that out. S1 has to be something times S0 on the intersection. So let's see. So for example, for this particular input point, I have to work out what S1 does to over here. But to work out what S1 does, you have to first make the second coordinate equal to 1. So this point in complex projective space is the same as this point in complex projective space, right? Because I've multiplied both coordinates by 1 over z. Now that I've got it in this form, it's in the right form that I want. So I know what S1 does. It just extracts, sorry, I've got it in this form here. It just extracts, it outputs this vector here in C2. This is a vector in C2, right? And now I want to write this vector, and I want to extract out, I want to write that as something times S1. You see, I want to write it as something times a vector of this form. Vectors of this form are where the first coordinate is 1. So I have to make the first coordinate 1 here, so I can take out 1 over z in front, and then I can write it 1 over z times this vector here. Okay, so this is my S1 vector here. So I've just, sorry, S0 vector. So I've just shown that the S1 vector is 1 over z times the S0 vector. So that's why that's 1 over z is my transition function. Because don't get confused, 1 over z featured quite a lot of ways. On the one hand, 1 over z featured as the change of coordinates function when we were doing the holomorphic charts in CP1. Now in a very different way, 1 over z is featuring as the transition function of the tautological line bundle over CP1. It's related, but they're not the same thing. Okay. So in order to check that this is a holomorphic line bundle, I need to check that these transition functions are holomorphic. This is a holomorphic function because if I were to use the holomorphic charts that I had before, the holomorphic charts would map this point in CP1 to z. So this would just be the function which sends z to 1 over z, which is a holomorphic map. Okay. So to use the other coordinate chart, it would be to map this point to 1 over z. So then it would just be the function of w goes to w. In either chart, it's a holomorphic map. If you're a holomorphic in one chart, you'll be holomorphic in the other. Okay. So it's definitely a holomorphic line bundle. What are the holomorphic sections of this holomorphic line bundle? Because that's the other thing we can ask, right? Whenever I've got a line bundle, I can ask what are its sections, global sections. And similarly, when I've got a holomorphic line bundle, I can ask what are its holomorphic sections. So what are the holomorphic sections of this? So we agreed earlier that once you've expressed your line bundle in terms of local data, that a section of that line bundle, you can think about it like this. A holomorphic section of the line bundle will be the following form. On U0, it must be some multiple of S0. While restricted to U1, it must be some multiple of S1. So that's how I'm going to extract out these functions on U0 and U1 respectively. They're going to be holomorphic functions. And I need that those functions agree to give me an S on the intersection. So I need this to be true. So that means that F0 over F1 must equal S1 over S0. And I know what this is. That's the transition function for the line bundle. That's 1 over Z. Okay. Now let's convert this now to the holomorphic charts, because on the other hand, I've got these bijections between U0 and C. So phi naught sends U0 to C like this, and phi 1 sends U1 to C like this. So this equation here, if I write it down, so at the moment, these Fi's are functions defined on U0 and U1 respectively. But now I want to pull them or push them forward, if you like, to functions defined on C. That's what these hats are. So this condition here becomes this condition here in terms of the hats. So I've calculated this as my final answer. So in other words, to give a holomorphic section of this tautological line bundle is exactly the same thing as to give a pair of functions, f0 hat and f1 hat. They are holomorphic functions defined on the complex plane. And they're not arbitrary, but they must be related in this way. That f1 hat, when evaluated at 1 over z, must equal z times f0 hat evaluated at z. And of course, this function only makes sense on C minus the origin, because otherwise I couldn't talk about 1 over z. Okay, so run through that argument yourself. At the end of the day, I hope I haven't made an error there, but this is what such a holomorphic section of the tautological bundle would correspond to. So let us try and find these functions, f0 hat and f1 hat, satisfying this equation. Well, since I've got a function, a holomorphic function defined on the complex plane, it must be defined on it's a holomorphic function defined on the entire complex plane, so it must be expandable as a Taylor series. But there's no singularities. So I can expand f0 hat like this. The Taylor series and f1 hat I can expand like this. And now I can sub that in to this equation. This is the equation which holds on C minus the origin. So I would sub in 1 over z into this expression here. And so it's going to give me this equation here. And now, what are the solutions to this equation? Let's see, am I making an error here? Let's see. Here I get a0 times z plus a1 times z squared plus dot, dot, dot. So the only way that you could solve this equation, because now we've got an equation of two Laurent series, right? This is a Laurent series, and this is a Laurent series, and they're defined over here. And two Laurent series are equal if and only if the coefficients are equal. So I would have to have that B0 here must equal the corresponding constant term here, which is naught. The B1 here must equal the constant term here, which is naught as well. So all the A's are naught and all the B's are naught. So that means that the only holomorphic section of this line bundle is just the zero section. Okay, so the tautological line bundle doesn't have any interesting holomorphic sections. On the other hand, the dual of the tautological line bundle does have interesting holomorphic sections. It has a two-dimensional space of holomorphic sections. That's something you should check. Okay. I've got a few minutes left, so I'm going to zoom through the remaining slides. Let's talk about connections on line bundles. So, suppose I've got a line bundle. What is a connection on a line bundle? I'm not talking about a holomorphic line bundle or anything, it's just a normal line bundle of a smooth manifold. It's just a machine, which I'll call nabla, which, given a vector field X on the manifold and a smooth section S of the line bundle, gives you back another section of the line bundle, satisfying these two properties. You think about it intuitively as a derivative of S in the direction of X. But you can make those derivatives in various ways, so you have to give this data as extra data on the line bundle. Okay, if you've got a connection on a line bundle and you've got trivializations for your line bundle, that means you've got these local sections SI, which are non-vanishing. And that means if I calculate the covariant, this thing here is called the covariant derivative of the section. If I calculate the covariant derivative of the section, SI, it must again be a multiple of SI because I've got a line bundle. So SI is a basis. So whatever this guy is, it's a multiple of SI. And I'll call that multiple alpha subscript I of X. And from these two conditions, you'll see that alpha I is a one form on UI. So from a line bundle with connection and from a local trivialization of the line bundle, I extracted out a bunch of one forms on each open set. Okay, now notice that on the intersections, UI intersected UJ, since Sj is equal to Gij times Si, if I take the covariant derivative of both sides and then I use this Leibniz rule, that's going to get me here. And that's going to tell me that these one forms are related like this. See, I have got a bunch of one forms on each UI, and this equation tells me how the one form on Uj is related to the one form on Ui. It tells me that alpha j is equal to alpha I plus something. And conversely, if you're given a bunch of one forms satisfying this equation, then you can construct a connection. So in other words, a connection on a manifold or on a line bundle over a manifold is just the same thing as a collection of one forms on an open cover satisfying this equation. Okay. You always have this way of writing global things in terms of local data and vice versa. Now, given a connection on a line bundle, I can calculate its curvature. What is it going to be? The curvature of a line bundle is going to be a certain two form on the base face. How does this work? Sorry, the curvature of a connection. The curvature of a connection is going to be a certain two form on the base face, and I just said it's equal to d alpha. What do I mean by that? Well, I take my local trivialization. That means I've got these local one forms alpha I, and all I do is I just calculate d alpha I. That's going to give me a two form defined on Ui. And now I'll show you in a second that that's actually a globally defined two form. So that's the definition, or what I'm writing here is the definition of the curvature of a connection of a line bundle. Okay, so what does this mean? So the point is that although these local one forms alpha I are not equal to each other on the intersection, their derivatives are, because we know that alpha j equals alpha I plus something. This tells us that alpha j is not equal to alpha I on the intersection because of this term here. But if I calculate d of both sides, then I'm going to get d alpha j is going to be d alpha I plus d of this guy. And I can use the quotient rule on that, and that's going to give me 0. So d alpha j equals d alpha I. So that means I can define a globally well-defined two form by just taking the d of alpha I. So it's a two form. To tell you what a two form is, I just have to tell you what it is on each open set. And as long as the rule that I'm giving to you is consistent on intersections. So on each open set UI, it's defined to be d alpha I. And that is consistent because on the intersection, that formula will agree with the formula that you're getting from uj. So it's globally well-defined two-form. The curvature of the connection. And here is a nice lemma that actually this curvature is not just any old two-form, it's an integral two-form. Meaning that when you integrate it over surfaces in your manifold, you get out an integer. At least I need to multiply it by a factor. I think I need to divide by that factor. Forgive me. Okay. So just to summarize here, what's going on is that earlier I said that there was a map. I said it was a bijection, but it's a map. There's a map from isomorphism classes of complex line bundles over M into the integer elements or the integral two forms. Those are two forms or de Rham cohomology classes having integral periods. And I wrote down this map earlier, but it was actually, remember, actually going the other way. Now I'm writing an inverse for this map. And the way that it's working is I'm going to take a line bundle L, and I'm going to equip that line bundle with a connection, any connection. Then I'm going to calculate the curvature of that connection. That's going to give me a two form, and that's going to be my de Rham cohomology class. Okay, and it turns out that it's not going to depend on the connection you chose, or the cohomology class won't depend on that. So this is a really nice way of extracting out the de Rham cohomology class representative of a complex line bundle. Okay, I don't want to carry on too far. Let me just end with a few sentences here. So, why have I spoken about line bundles right now? Remember our previous, let's take a few steps back. The course is on complex manifolds. Good. What's the nicest example of a complex manifold? Is a Kähler manifold. Kähler manifold is where you've got a complex manifold and a Riemannian metric on your manifold. And those two structures get along with each other. So that's called a Kähler manifold. What's the nicest example of a Kähler manifold? Well, remember that your Kähler manifold was defined by this two form, this omega, which was the fundamental two form of the metric, if you like. So this Kähler manifold was a complex manifold equipped with a compatible symplectic form. What is the nicest possible symplectic form you could have? You'd want one that's integral. In other words, whose integral over surfaces in your manifold is given by integers. So, and then you say, okay, suppose I've got an integral Kähler manifold, meaning that the Kähler two form is integral. That's a very nice Kähler manifold. If that's my situation, then there will be a line bundle L living over my manifold with connection, and the curvature of that connection will give me that two form omega. So in other words, the process of this course has been just giving you nicer and nicer examples of complex manifolds. First of all, I just said what an almost complex structure is. Then I said what a complex manifold is, which is a nice kind of almost complex manifold. And a Kähler manifold is a very nice kind of complex manifold. And now I think it's called a quantizable Kähler manifold, is where the Kähler form is integral. And that means it can be expressed as the curvature of a line bundle of sitting over your manifold. So that's really nice. So all the geometry is now coming from structure, geometric structure living on the manifold. So the nicest examples of Kähler manifolds are coming from line bundles with connections sitting on top of your manifold. That's just the way I want to end it. We don't have much time to get into what all that means, but you can read more about that in Le Floch chapter 3 and 4. And now, I thank you for sticking with me all this way.
Thank you very much, Bruce. That was a very cool way to end.
Yeah, thank you.
Okay. Cool, guys. Yeah.
Yeah, I thought that was a nice way to wrap it up.
Okay.